All right, so I wanted to do some notes over kinematics. That's kind of what this unit's called. And it's pretty much the study of motion. We're going to be looking at one-dimensional motion or 1D motion. And so why I guess is physics is the study of the world around us, and the things around us are moving. In this chapter, in this unit, we're going to be looking at how things move. How things move. We are not going to be analyzing why things move. So we will not talk about what got the object moving, right? That'll be for a different chapter. But in this chapter, we'll just look at when objects move, how we describe that motion. So the other day in lab, we started with position, and we said that we had the variable x being our variable for position. And we also talked about the fact that it could be xi for initial position. And I mentioned that sometimes we like to use the variable, this is a subscript where I'm writing the I or that 0, and this is also initial position. And we pronounce that x naught. So I guess I can write that maybe underneath this. So we say it x naught. In math class, we sometimes, in here we like to use xi and xf. Sometimes in math class they use x2 and x1, and I'll get to that in a second. So this is final position. And then we have displacement being delta x. And so this is xf minus xi. You could also say it as x2 minus x1, which shows up in math class. Physics is more of an application class, so we are applying the math here, so we like to be a little more descriptive than just 2 and 1 a lot of times, and so we like to use xf minus xi. So that's one of our important formulas, because delta x is equal to displacement, this change in position. Okay, so other things to note there. I would just say that displacement is a vector. So we can describe it as, sometimes write it with the vector symbol above it, this arrow over its head. And what I mean by a vector is something that has magnitude and direction. Maybe I should say equality. I guess something's fine. Something with magnitude and direction. So how do we know this, right? And well, I guess maybe an example would help. Well, first of all, we know it has direction because of the sign. And And that's probably new for you, coming from math class where we had negative numbers that didn't really mean direction, right? We just thought of them as negative numbers. But here, the negative sign indicates a direction. So a lot of times we like to call right positive and left negative. And then the magnitude would be whatever the amount is. So when I think of magnitude, magnitude, we're thinking of how large or small the number is. All right, let's see if I can get rid of this. Get this out of the way. Oh boy, I don't know if I can. Okay, there we go. All right, so vector is something with magnitude and direction. Not everything that has a sign is a vector. But it is a good indicator that if it has a sign that it may be a vector, because the sign will tell us which way it points. So vectors, something like temperature can be negative, but isn't a vector. So vectors point in three-dimensional space. So you could say, if we had a displacement, let me go ahead and write this. Delta x equals xf minus xi. I'm just going to go ahead and draw a number line really quick. And we'll say that the object has an initial position of, I don't know, I'm just going to make a number up, positive 5. And this is xi, and then xf is, we'll keep it positive as well. We'll say positive 2. All right, so the object has a xf of positive 2. So if I think I'm going to need another page here. Let me see if I can add one in. All right. So if this object has, so if we do the calculation, right, delta x equals positive 2 minus positive 5, right? This is 2 minus 5. So we see that this is going to equal negative 3. So what does this mean, right? Well, first of all, we can see why displacement, right? If I draw this vector hat over its head, why it's a vector, right? Because what this answer indicates is that the displacement of the object is equal to 3 units, whatever that is, centimeters or whatever, to the left. That's what that negative sign says. So this object started at positive 5 right there, and then displaced 3 units in this direction right here. I thought that would help to see it in yellow, and I don't think it really is helping. It displaced 3 units in that direction from positive 5 to 2. So I don't think that's helping either in black. I'll try blue. All right, so displaced like that to the left. And that's kind of the idea of displacement. So it is a change in position. It contains a direction. And I sometimes like to think of displacement as the net movement in a direction. So let's write that down. Okay, so This is kind of hard to look at with all the, I feel like everything is kind of together. Good. So this is the net movement in a direction. What else can we say about displacement? I guess we can start to talk about maybe distance and how it's different than distance. All right, distance is the movement in any direction. It is always positive. So direction doesn't matter, it's always positive. Therefore, it's a scalar. Now, what's a scalar? Well, a scalar is something that has magnitude. Has magnitude, but no direction. So let me go ahead and add another page here. Oh boy. Let's see. Oh geez. All right, so has magnitude but no direction. All right, so temperature is an example of a scalar. Now you might say, well, how is that, right? Because it could be -5 degrees outside. -5 degrees Fahrenheit, right? Outside. And you'd be like, there's a negative sign, therefore, and there's a magnitude 5, so therefore why isn't it a vector, right? So temperature is a scalar because it has magnitude but no direction. When we say direction, we mean that it does not point in three-dimensional space. So that's what we mean here. So I can write that, add that here. Does not So you couldn't say 5 degrees Fahrenheit east. You couldn't say 5 degrees Fahrenheit left. And that just wouldn't make sense. Whereas -3 units, right? You could say 3 units to the left, 3 units east. And so this is why this is a vector. So vectors, if we go back to, we said this up here, vectors point in three-dimensional space. And this is what I meant by that. All right, so now you can kind of see the difference there. I mean, some things are obviously scalars. Like another example of a scalar would be page number. That would be another example of a scalar. Things that are vectors, if I go displacement, where is that? Vectors. Displacement is obviously a vector. And let me see if I can add some examples in blue. Examples. We're going to actually use a lot of vectors in this class. Things like velocity, acceleration, force, things that are scalars, temperature, page number. I already have that. What else can we say? I would say work is a scalar, which is a change in energy. That's kind of a tough example. Oops. Energy. Distance, right? We already said. And then I guess another one would be speed. Okay. So, good. We're getting some examples there. Let's go a little further here, and let's talk about, let me add one more page in. Just make sure I have enough room. I don't think I'll need it, but add it in anyways. So when we talk about, in this class, we're going to add on to displacement and distance. So we have distance is a scalar, displacement is a vector, but then we can make them both rates. A rate is something, we'll say a quantity or a quality divided by a unit of time. So speed is a rate, and speed is equal to distance divided by time. Time is a scalar, so we can add that up here to our examples. Let me get a different color. Go purple. All right, time is another example. All right, so here we have two scalars, right? Distance is a scalar, time is a scalar, so speed is a scalar. Speed doesn't care about direction, right? When we talk about speed, we're like, we're traveling 25 miles per hour, and that's the speed limit, right? We don't care which direction we're going in, and so that makes sense that distance is direction independent, right? Doesn't matter, and so speed is too, and time is as well. Time only goes forward, the arrow of time, and so anyways, time is a scalar. All right, so well, what would happen then if we took displacement and put that over time? Well, then we would have velocity. And we can write both of those slightly differently. Usually with speed, I don't write it I don't give speed a variable. Sometimes we give the distance the variable d and time the variable t. And then for displacement, or for velocity, I like to give it the variable v, and displacement is obviously delta x, and time is t. Notice how I curl my t's. When you write the variable time, please curl your t's. That way, when I say curl it, I mean like that, right? And then that way, it doesn't look like a plus sign, which will look like that. So we do like to add time in this class. So we have equations with time in it where we're adding. So we don't want to confuse our t's with plus signs. So please do that. But check this out, right? Since displacement is a vector, guess what velocity is? A vector. So you can kind of see the logic there now. All right, good. So that's just some rough notes over position over distance, or position over displacement, which is a change in position, over distance, which is how far something moves, or how far something travels. I think I have that on there. Movement in any direction. I'm going to add that in there. How far something moves. And yeah, and I think that looks all right. Okay, so just getting some ideas out there about describing one dimensional motion. Let's go to a more official looking note guide that I usually give out, and here you can see we started off talking about average velocity, and so now we're gonna make a difference here between two types of velocity, and one is going to be v average, or average velocity, and one is going to be v instantaneous. And we'll try and understand why they're different, right? And over the course of this note guide. So we'll use both in class, and I'll try and explain the difference, or I'll try and point that out when we do use them. All right, average velocity is represented by what symbol? And I just wrote that above. Average velocity is v average, just like that. Write the formula for v average 3 ways. Okay. This might be a little, well, we already kind of did this a second ago, so we'll go ahead and try it again. Whoops. All right, so V average is equal to delta X over delta T. We can say V average is equal to delta X over T. I don't always write the deltas on my T's. We can say V average is equal to displacement over time. All right. How can average velocity, oh, typo, that should be B negative. How can average velocity be negative? It can be negative because negative indicates what? Well, the negative sign indicates direction. Ugh. Let me see if I can get rid of this again. Jeez, I'm terrible at using this. Let's see. All right. Good. Explain why average velocity isn't average. Okay, this is a little tougher to do. Average velocity is an average because it accounts for the times that maybe we aren't moving at that velocity. Let me get a different, or split this up somehow with some green here. Okay, so average velocity accounts for the times we are moving other velocities. All right, is this realistic? Put in terms of a car ride. All right, so on your car ride to school, let's say you drive to school and you drive maybe just down Platte Road, right? And you're going down Platte, and you travel mainly 60 miles per hour down Platte. But this wouldn't be your average velocity because maybe you got stuck behind a slow car. Maybe you got stuck behind a bus. Maybe you were at a stop sign, right? There's plenty of stop signs. There's traffic lights. So maybe your all-in-all average velocity on your ride to school, even though Platte is mostly 55. I mean, there's some areas where it's 25 over by Simons. And so we would expect to see an average velocity of what? Probably 40 miles per hour on your car ride to school, right? Just a guess, right? And so is it realistic, this average velocity? We would say yes, because it accounts for running out of room. It accounts for stopping, slower speeds. notice I kind of switched into using the word speed here. Sometimes I'll do that, and you got to keep in mind that we are very particular with the difference between speed and velocity in physics class, but sometimes we don't care about that, right? All right. Anyways, average velocity is not literally an average of final and end velocities. Example. All right, so this is a good example, and maybe I can get another piece of paper here in between this, because I think this would help explain this. So let me move down here. Why can't I? Okay. So let's see. It's not what I want. This has got to be difficult. Okay. All right. So we'll add a page. All right, so check this out, right? Okay. So let's look at this. And I think this is a good example that'll kind of be like, because I think a lot of you are probably sitting there thinking, yeah, average velocity, just add the velocities together, divide by 2, right? And is that all it is? Because if that's all it is, I'm probably wasting your time. All right, if you take a trip where the first 50 miles you drive 50 miles per hour. Okay, so let's look at this. Let's say you're going on a trip. All right, here's home. All right, it's a great sketch. Here's home. And you're going to go on a trip, and it's just one road, no stops or anything, just straight shot. And then I don't know where you're going. You're going to grandma's house. All right. Okay. Gma's house. All right, going to grandma's house. And it says if you take a trip where the first 50 miles to go to grandma's house, so this is going to be about half, because I think it's going to be 100 miles to get to grandma's house. So we'll write, let's see, get a little color in there, 50 miles. The first 50 miles, you're going to travel 50 miles per hour, all right? You got to go there for dinner or something. All right. And then the second 50 miles, you're going to go 100 miles per hour. You're going to step on it, right? And you wouldn't really drive that fast. This is, just a fictitious problem here. All right. So another 50 miles, you're going to go 100 miles per hour. Oh, yeah. All right. And then it says, what is your average velocity? So it's real easy to just say, well, so you're like, oh, I know averages, right? Math class, 50 miles per hour plus 100 miles per hour divided by 2. 150 over 2. You're like 75 miles per hour. Physics is easy. All right. But it's wrong, right? So why is that, right? Well, let's think about what our formula for average velocity was. And it said V average is equal to delta x over t, right? So V average is equal to, well, delta x, that would be xf minus xi. And then t, well, this is kind of like t total, right, for the whole trip. And what you're starting to see then is that t total, there was really 2 segments there, right? There's kind of like a T1 and a T2, because you were traveling different velocities at those for those different segments of the trip, right? So when you stepped on it for 100 miles per hour for the last 50, you were going to get there. You were going a lot. That's a smaller segment of time, right? So I'm saying that T2, let me get another color here. Let's go with some orange. T2 is going to be much smaller than T1, right? Because you're cruising. And so let's go a little further with this. So we can say XF, final position is going to be 100 miles, right? Initial position, let's start at 0. Why not, right? If they don't tell us, we can always start at 0, and that's fine. And then what are T1 and T2? Well, we're going to have to solve that, right? So we know that V, or maybe I should, or we can just think about this logically. Let's not even, I don't want to hit you with another equation. Okay, if you travel 50 miles per hour, if you travel this segment right here, 50 miles per hour for 50 miles, how long does that take? And you should be sitting there saying 1 hour. All right, so we know that this is 1 hour. And then if you go 100 miles per hour and you travel 50 miles, how long is that going to take? Well, 100 miles per hour, 50 miles. You know what we could do with that is we could just do a conversion factor, because that's kind of tough and maybe you don't see it. Maybe you don't see either of them, right? We could do a conversion factor for both technically if you wanted. So we have 50 miles and we have a conversion factor of 50 miles per hour. 50 miles per 1 hour. Notice what I did there, right? A little conversion magic. Miles cancel. We're left with multiply the top across, 50 times hours over 50. We get 1. Our answer is 1 hour. We already knew that, right? I was more interested in the other leg of the trip. Okay, in the other leg of the trip, you're going to go 50 miles. You're going to go 100 miles per hour. Notice how I can write it. You just flip those conversions any way I want, right? And that's what we thought, right? I think it was kind of obvious. It was going to be, right, half an hour. All right, so for the second leg of the trip, it's only going to take a half hour. I think we were writing in green up there. All right, so half an hour. Okay, so, but we said, yeah, that's fine. So total time for the trip is T1 plus T2. So we're saying an hour plus a half an hour, which is going to be 1.5 hours. What's 100? And this is where I'm running out of room. Shocker, I'm always running out of room, I feel like. 100 miles per 1.5 hours, right? What does that equal? Get our calculator out. I think it's 66.67. Why can't I do that in my head? Yeah, 66.67. Aha. MPH, miles per hour. And so now you can see, right, that maybe physics isn't as easy as it looks. And this is why we have to trust our formulas. So this is the right answer because we were traveling different speeds. We were not going the same amount of time. When we do it this way, the unhappy face way, we were assuming that we were traveling equal amounts of time, right? And we weren't. We weren't traveling those speeds for equal amounts of time. We were going 100 miles per hour for less time and 50 miles per hour for more time. In this average velocity formula, takes that into account. And that's why the average velocity, instead of being in the middle, was actually closer to 50 miles per hour, right? It was not 75, it was closer to 50 because you were traveling a greater amount of time at 50 miles per hour. Okay, hopefully that makes sense, that reasoning for why. All right, and then the math, right, proves it. The math, the formula takes that into account and proves that. All right, good. Okay, another word that does not quite mean the same thing in the language of physics is speed. Why? Well, speed is not direction dependent, right? Speed is a scalar. And direction doesn't matter. All right. Why do race cars have speedometers and velocipedometers? You know, this is a question that I feel like I know the answer to, and then I forget the answer to it. But I think it's so that they can look at how fast they're going. And somebody in my class knew this last time, and I wish I could remember the answer they gave. And they knew it right off the bat. And I think it was something along the lines of, so they know how quickly they're moving in a certain direction, say towards the finish line, or when they're navigating a turn. I thought there was a better answer than that. So I'm going to leave that blank right now and see if any of you can come up with that answer. I'm just going to write, tell me. Sad Mr. Rodriguez face. All right. I like learning, so I would love to know the answer to that question. This graph paper. This is horrible. All right, so we're going to have to make a graph here of position versus time. And I really despise this small graph paper. I know it's not going to work. I don't know if I can add a page of graph paper. There was a grid somewhere. I just don't know what I'm doing. Let's see. Dang. Paper. Ooh. Let's see. Oh, yeah. Oh, that's nice. Okay. All right. Amazing. Okay. So what we're going to do is we're going to make a graph here. And let's go ahead and you can draw it right on the small graph paper, but it's so horrible to use. And if you don't want to use it and you want to just use Cami or something, or you can, I don't know, just write it on a line sheet or a blank sheet of paper, anything. I don't know, that graph paper is just annoying to me. So let's say we have a graph like this, and we're making a graph of position versus time. So one of the things about physics is that when we make position versus time graphs, I can always tell if somebody has had physics before, because they would know that every time, in this class, time is always on the x-axis. I think it's because time is the independent variable. I think the independent variable, which is just going to go forward, it's just time's going to do its thing, is going to always go on the x-axis. The dv, or dependent variable, I should probably write that down because maybe that's going to be useful for you someday. I don't know. But the iv is time, and the dv is the dependent variable, depends on the independent variable. So as time goes on, what happens to the position, right, is what we're interested in. So we have this graph. Notice the use of parentheses here, right? I put parentheses and then a unit, right? Meters and seconds, which shouldn't be a shocker. Those are our favorite units to use in this class. And then we're going to graph some points. We are given a data table up here, it looks like we have, when it says when the object is at time 4 seconds, it's at position 4. So I'm just going to come down here and write a mark at 4. And this is, I'm going to go ahead and put the number 4, and then go up 4 right here and write the number 4. And then I'm going to put a point right here. Okay. Then I'm going to do the same thing for the next data point. And you could, mark every number down if you really wanted to, but I ain't got time for that. All right, 5, 6, 7, 8. 5, 6, 7, 8. All right, and we'll go put a point at 8, 8. I think when you say that 8, 8, the x variable is always first, by the way. It's been a while since I've had a math class, but I'm pretty sure that's right. 12 is the last one. Let's see. And then, ooh, this is turning into an eye test. All right. So put that point right there. Okay. I think that looks pretty good. Then we're going to take another color. I don't know, maybe what color haven't we used yet? I like brown, but maybe pink. I haven't used pink yet. All right, and then I think there was one more point though I forgot, and I forgot to write this on here, and that's 0, 0. So that is also going to be a point of interest. So we're going to put one at the origin, and then I'm going to go ahead and get that pink. All right, and draw a straight line. All right, why the heck does any of this matter, right? Well, okay, let's go to this next question, question 10. What's the slope? What's the formula for the slope of this line, right? In math class, we had the equation of a line, right, which was y equals mx plus b, where m was the slope and b was the y-intercept. And then we said that the slope was equal to rise over run. And kids always want to, run spelled R-U-N. Kids always want to tell me that, but it's like, well, what's rise over run is what I like to ask back. And then they're like, I don't know, and then they kind of like, and some kind of give me an answer that works. And, but if you remember, right, it was how much you rise, the change in y over how far you go forward or back. Yeah, which was the change in x. And that's all good, right? That's fine. Well, now you can kind of see that if slope is delta y over delta x, well, what's on the y-axis? Well, position, right? Ooh, what's on the x-axis? Time. This should look familiar, right? What the heck is this? You should say what? Well, if you were paying attention on this long lecture of me rambling, you should say that is the average, right? All right, so the average velocity is the slope. Now, it's not the slope of every graph. You can't just go around in math class and just say, oh yeah, the slope, you mean the average velocity? No, you can't just like interchange the two words. No, it's the slope of a position versus time. I don't know why I'm writing like, let me erase that and write that up there. I'm erasing the graphic with that? Okay. Is the slope of a position versus time graph. All right, so that's awesome. So anytime we graph position versus time, the slope is velocity. All right, so now we have a way to quantify or calculate average velocity, and we have a way to graphically show the average velocity of an object by making something called a position versus time graph. That's pretty awesome. Okay, two ways to see or understand average velocity. All right, so we'll call it there. Next time we'll talk about instantaneous velocity and how the two are different, right? Okay, that's it.